Good morning. This is class 3 of our module 4 dealing with varying currents. In the last class, we have studied about the definitions for alternating current, then alternating EMF, etc. So, today we will discuss about mean value and root mean square value, that is RMS value of alternating current, that is AC. So let us begin with the mean value or average value of alternating current. You know that an alternating current flows half time in one direction and the rest in opposite direction. See, this is how you draw an AC with the time along this axis and current along the y-axis. So it flows half time in one direction and another half time in the opposite direction, like this. So this is the time period. This, if t is the time period, then this one will be t by 2, then this half will be again t by 2. So this one, the positive half in the positive direction and the negative half in the negative direction together will form one complete cycle with the period t. Okay, so for one complete cycle, the average value of AC will be 0 because positive half and negative half, that will get cancelled. So for a complete cycle, the average value of AC is 0. However, there is a mean value over a half cycle, and that is termed as mean value of AC. Now our aim is to find what is that mean value, or we have to derive an expression for the mean value of AC. So mean value of AC is given like this. I mean is equal to 1 by t by 2. T is the time period. Since we are calculating over a half cycle, we write, instead of t, we write t by 2. Okay, so I mean is equal to 1 by t by 2, and you will integrate over 0 to t by 2 because half cycle. So only t by 2, small I dt. What is small I? Instantaneous value of current. Okay, capital T is 2 pi by omega. Now for this value of I, here you have to substitute these two values. Instead of this I, you have to write this. So that is written here. Then T is 2 pi by omega. So substituting here, instead of T 2 pi by omega, it will be omega pi by pi. Similarly for this T also, you have to substitute 2 pi by omega. So it will reduce to pi by omega. That is how you obtain this expression. Now omega by pi is kept as such. I0 is a constant, so that is taken outside. Then what is integral of sine omega t? Minus cos omega t by omega. Okay, so minus cos omega t is written here, that by omega, that omega is taken outside. Then you are applying the limit which is given here, 0 to pi by omega. Then next step is omega and omega will get cancelled. So I0 by pi is kept here. Then you are applying the limit. This minus is taken outside. Okay. Then applying, instead for t, you have to apply the limit. So cos omega, instead of t, you have to apply the upper limit, pi by omega. So it will be cos omega into pi by omega, that will be cos pi. It is written here. Minus, what is the lower limit? Cos omega into 0, that will be cos 0. Okay, then it is again equal to I0 minus is there, I0 by pi. What is cos pi? Minus 1. Minus cos 0 is 1. So you will get substituting, you will get 2 pi by pi I0. What is the value of 2 by pi? 0.637. Okay, that much I0. Thus you got the value of the mean value of AC for a half cycle as 0.637 times, or 63.7 times the peak value. What is the peak value? I0. So mean value is 0.637 times the peak value I0. So but always remember, it is 0 for a full cycle. So if you are asked to write the mean value of AC over a full cycle, it is 0. If it is the mean value of AC over a half cycle, it is 0.637 I0. Okay. So all these integrations are very simple. So it is very easy to follow. Now let us So that is the expression for the mean value of AC. Now we have to find the root mean square or RMS value of AC. The only difference is that instead of I, you have to write I square. Okay, now it is defined as square root of I square during a complete cycle, where I is the, as already said, it is the instantaneous value of alternating current. Now the expression to find the average value of I square over a complete cycle is this: I square bar, that bar sign actually denotes average, okay, is equal to 1 by T. Why it is written 1 by T? Because you are calculating it for a complete cycle. So it is T instead of T by 2. Again, for integration, the limit is from 0 to T. Instead of I, you are writing I square dt. So hope it is clear. Then as usual, as said before, instead of I, you are substituting I0 sin omega t. So here, instead of I, you are writing that since it is the square, you just square it. Then instead of t, instead of this t and the integration t, you have to substitute 2 pi by omega. So it will reduce to like this. This is exactly what we have done earlier. Then here I0 omega by 2 pi is kept as such. Then I0 square is a constant, it is taken outside, limit is kept as such. Then the sine square omega t, it is rewritten as 1 minus cos 2 omega by 2. Cos 2, 1 minus cos 2 omega t by 2. Why? Because sine square theta is equal to 1 minus cos 2 theta by 2. There is a formula like that. So instead of sine square omega t, they are using 1 minus cos 2 omega t by 2. Now everything is written as such. This 2 is taken here. So it will become omega by 4 pi. I0 square is kept as such. Then you are applying the limit. How you are applying the limit? You are just splitting. That is integral 0 to 2 pi by omega dt minus integral 0 to 2 pi by omega cos to omega t dt. Okay. So the first part, that is integral 0 to 2 pi by omega dt will be t. So t is written there minus what is integral 0 to 2 pi by omega cos 2 omega t. Integral cos 2 omega t is sine 2 omega t by 2 omega. Okay, so that is written here. Then the limit is kept as such. So on simplification, omega by 4 pi is kept as such. I0 square is kept as such. Then instead of this t, you are applying the upper limit 2 pi by omega. So it is written here. Then when you apply the lower limit, everything will become 0. So it's not there. So finally you will get the RMS value of AC over a complete cycle as I0 square by 2. So that is actually I square value that you obtain. I0 square by 2. So what will be IRMS? It will be I0 by root 2. Okay, that so this 1 by root 2's value is 0.707. Then I0 is kept as a. So the value of IRMS or root mean square value of AC is 0.707 times or 70.7 times the peak value. Okay, so mean value was 0.637 I0, whereas the RMS value is 0.707 I0. Now this is a question that is probably asked, that is why 220 volt AC is more dangerous than 220 volt DC. Okay, so we know that as alternating current, alternating EMF or alternating voltage is given by the expression ERMS equal to E0 by root 2. Okay, so in our houses it is said to be the AC is supplied at 220 volt. Okay, that we know, 220 volt AC, we are getting it for domestic applications, but it actually refers to the RMS value of alternating voltage. So the 220 volt that you get in your house is the RMS value of alternating voltage. Then what will be the peak value? It will be actually root 2 times VRMS, and that will be approximately 311 volt. Okay, that is peak to peak voltage of domestic supply is minus 311 volt plus 311 volt. So 220 volt is more dangerous than 220 volt DC, because it is coming like this, a value around 311, which is much higher than 220 volt. So that is why we say 220 volt AC is more dangerous than 220 volt DC. So when they ask a question like this, you have to write this full paragraph. Okay. Now, RMS value of AC has some special significance. That is, if an AC passes through a resistance R, then the rate of production of heat, that you know, I square R low, P is equal to I square R. In place of I, you are writing I0 sin omega t. You are just squaring and writing R as such. Then you are taking the average value. For finding the average value, you just put a bar sign over P. So it will be like this. P bar equal to this one, average value is written like this, I square R average. So here I0 square and R is a constant, so it's taken outside, and then you are averaging only the value of sin square omega t. Okay, now the average value of sin square omega t is found to be half. So the average value of heat produced will be I0 square 2 by R. RMS value of AC is again defined as direct current which would produce heat in a given resistance at the same rate as the alternating current. Study that definition also. Now another definition that comes is what are phases and what are phase diagrams. So here you have to study two definitions. One is what are phases and the other is what is a phasor diagram. Okay. The current and EMF vectors are called phases. That is, current vector and EMF vector are together called by the name phases. That is one definition. Now, a diagram representing alternating current and alternating voltage as vectors with the phase angle between them is called phasor diagram. So, study the definition for phasor and phasor diagram. Next, we are going to consider various types of AC circuits. So here, to begin with, we will consider a circuit containing only resistance. So here you are applying an alternating EMF, that is E equal to E0 sin omega t. This circuit contains only resistance. So that is a circuit. So by Ohm's law, we know it is V equal to IR. Instead of V, here you have an alternating EMF or alternating voltage given by E0 sin omega t. So as per Ohm's law, this is actually V equal to IR. That is E0 sin omega t equal to current in the circuit into the resistance in the circuit R. So from this you can find I as E0 by R sin omega t. Now E0 by R, you can write it as I0, which is actually the peak value of current in the circuit. So the above equation reduces to I equal to I0 sin omega t. So when AC voltage is applied across the resistor, what happens is that both current and voltage will vary as sine function. See, variation is in the form of a sine wave. Current also varies in the form of a sine wave. Similarly, EMF or voltage also varies in the form of a sine wave. Another important point that you can note here is that in a circuit or in an AC circuit containing only resistance, you can see that from the first figure, current is always in phase with applied EMF. There is no phase lag. Both current and EMF are in phase. That is, increases to a maximum value, decreases, then increases in negative direction and again decreases. Similar is the behavior for EMF and current. That is, both of them are in phase. Now, this behavior is also expressed in the phasor diagram. This is a phasor diagram. See, both EMF and current, the variation is linear. That is, both EMF and current are in phase. Okay, so the peak values E0 and I0 are represented by phases. See, phases, they are represented by like that, rotating anti-clockwise with angular velocity omega. It is marked here with respect to horizontal reference axis. Their projection on the vertical axis gives the instantaneous value of E and I. See, this is the projection. This is the peak value of current and voltage, and their projection on the vertical axis gives instantaneous value of E and instantaneous value of I. Okay, so that is enough for today. Please go through the derivations for mean value and RMS value of AC, then a definition phasor and phasor diagram, then the representation and explanations for an AC circuit containing only resistance, that is how EMF and current varies. Okay, thank you.